Hello everyone, my name is Saikat Dey. I am an assistant professor in the Department of Electrical and Computer Engineering at University of Central Florida. I joined this fall, like fall 2025, and I'm in the process of starting up and building up my lab infrastructure over here. And I'm genuinely looking for interested students who are interested in my research. And I'll give a brief background of what I do and what I plan to do by this presentation. So my research interest actually lies in the domain of high-frequency power electronics, multi-order power converter systems, which can be applied in the fields of space electronics, renewable energies, grid integration, transportation, electrification, and many other fields. I majorly work with wide bandgap-based power electronic converters and their modulation techniques, some of the magnetics, some of the elements of magnetics, and other things also. Okay, now talking about my background, I did my bachelor's in electrical engineering in 2018 from India. Following that, I joined Tego Technology, a fabless gallium nitride semiconductor firm who develops gallium nitride power ICs. Um, and they worked there as a power electronics design engineer. That company got acquired by Global Foundries recently. Following that, in 2020 fall, rather December, I joined Arizona State University for my systems engineering PhD degree. I completed my PhD as well as my master's from there. While I was in Arizona State, I worked with Lucid Motors as an power conversion control intern, and I have some of the contribution in the Lucid vehicles um, charging software. And I joined this department, as I told, this fall, 2095. This slide actually articulates some of my research over the years. So it's the timeline of the 2000 starting of 2019 to now, what kind of power converters I have developed over the time. Starting from a all GaN 65 watt type USB Type C wall charger. This is the charger, or this is the converter rather, that sits inside your MacBook charger. I mean, very similar. What it does, this MacBook charger does the same thing. It is just in a very much smaller form factor. And that time it was industry's highest power density wall charger. Following that, I joined my PhD and I started working on the other hardwares. Um, the first hardware on the leftmost side is the high density EMI filter for more electric aircraft. In this project, I actually worked with some of the EMI filter design techniques and how to propose a volumetrically optimized EMI filter design for any kind of power converter like this. Following that, I worked on some high temperature power electronics as well. So the power converter that you can see on next is a 250 degrees Celsius operable 200 watt non-inverting buck boost converter. We tested this converter to a elevated temperature of 250 degrees Celsius, and at this temperature, designing the electronics uh, needs a lot more constraints to keep in mind, as well as a lot more characterizations to make for the magnetics, for the capacitors, and for the active devices as well. Mm. Following that, I started my work on the multi-active bridge type of topology, and that basically says it's a multi-port power converter. In generally, the power converters are two ports, one input, one output, but multi-port power converters has multiple, maybe one input, two output, or more than that output, or in input or um, in outputs, basically. So this was a three-port converter uh, for a space station power supply. The one port was PV, another port was DC distribution bus at 120 volts, another port was 28 volts battery. Um, I propose this topology. This is an integrated power converter which saves a lot more space compared to two cascade power converters. But we actually invite some of the control complexities. However, if we can actually model the converter well and then control it very strategically, make the switches go through soft switching so that the switching loss as well as the conduction loss is minimized in the switches. In that case, we can actually get more efficiency compared to the state-of-the-art techniques. We got 2.6% more efficiency compared to the state-of-the-art, as well as 30% reduction in the volume for the same switching frequency operation. So we achieved around 150 watt per inch cube power density with 97% peak efficiency for this converter. This was the major task of my PhD. We extended this 3-port converter to a 4-port converter also with the same topology. It is a QAB, quadruple active bridge type of converter with just one transformer. Following that, I worked on a hybrid solar microinverter, which has PV in one side, the grid in another side, and another port comes to a battery. So the battery backup is also present. This was majorly developed for a residential application for the off-grid communities in Navajo Nation, USA. And this was a 1.5 kilowatt solar microinverter. With the proposed topology of like integrated topology of triple active bridge, we achieved around 2.1% average efficiency benefit. And this also employs all gallium nitride based switches. After that, there is a 2-port microinverter. There's a DC to AC microinverter using a single stage topology. Traditionally, the topology has been a DC-DC in the DC to AC, DC-DC in the first stage, and then the DC to AC inverter in the second stage. However, I just applied a single topology, a single power conversion stage, and that makes the cost as well as many other things more simpler, while achieving a much more efficiency of 97% with my proposed control techniques. Uh, Following that, I worked on a neural network-based power converters parameter estimation algorithm and how to integrate neural network in a power electronics converter operation. So it was a dual active bridge converter for which the converter's circuit parameters, the inductances, capacitance are actually calculated or estimated by the neural network, trained neural network, and it sends back to that data to the controller, and the controller updates the control system based on the estimated parameters. So it is a whole neural network in loop control system. So I plan to extend this kind of work in future as well. The last work of my PhD was on a 1.5 megahertz dual active bridge converter. This was for a radar or pulse load power supply, and this actually achieved a power efficiency of more than 96%, and power density of 200 watt per inch cube. This was also all GaN topology in a very small form factor. This converter is the size of an iPhone 13 actually, which can process 1.5 kilowatt of power. Okay. Coming down into this slide, I'll talk about some of my research direction moving in future. So the key focuses of my research group will be on 4 topics. One is converter topologies and devices, where I'll try to innovate newer converter topologies using new devices like bidirectional, monolithic bidirectional switches. And also, I'll try to innovate different switching modulation as well as control techniques for multi-order power converter systems. The modulation strategy, there is a scope of innovation in the modulation strategy so that the switching action happens in a way that the sub switching can be elongated over a wide gain and voltage range for the converter, and the converter efficiency can be maintained over a wide range of operation. The third topic will be on passives and EMI. I will try to investigate different passives, including magnetics as well as capacitors for high temperature, low temperature, as well as for high frequency operations. And so final topic will be on the AI or ML techniques, so that we can newer AI and ML techniques for parameter estimation and monitoring and health monitoring and reliability analysis of power converters. I invite collaborative research from the domain of power electronics, power systems, microelectronics, radiation effects, and ASIC designs, etc. AI/ML expertise, material science expertise, the electromagnetics expertise, and robotic expertise, and together we can actually focus on these target applications. One and beyond clean energy grid integration. Another would be space and defense power supply. The third will be on AI applications in power electronics and multiple different domains, and how we can actually use the growth of AI in advantage for power electronics. And then finally will be multiple power converters for EV charging, data centers, and microgrids. So these are the shorter plan of mine to concentrate on. I would invite masters, bachelors, as well as PhD students, and definitely outstanding postdocs to join my group. I am starting my group at Research 1, 313 for now, and I'll move to 316 in future. So I invite all of the students to contact me if they're interested in my research, and I'd be happy to chat. Thank you.